applications of the derivative. So assuming that we have passed that stage of learning how to differentiate, then we can use differentiation as a tool to study functions. It is frequently the case that the derivative is simpler than the function itself, and the questions that we're asking of it are much simpler than the function itself. So increasing and decreasing behavior is hard to verify. In the meantime, if we do have the derivative available, the question becomes simply the sign of that derivative, so positive, negative. So it becomes purely algebraic. If you make that calculus step of differentiation, then after that you don't have to worry about calculus anymore, because the algebraic part that we carry out over here is nothing but algebra. So this is the calculus part. Okay, the calculus part is to differentiate. This one was very straightforward, and it's just sum rule in the power formula. But then non-calculus, I would say non-calculus, this is just algebra, is determine the sign of the derivative. So it still takes some work depending on the complexity of the function, but you split the function into its domain into the intervals, and appropriately, and then on those intervals the sign changes, okay, from one to the next. Okay, so that's what happened here. The derivative was fairly simple, only two factors. You can either, I would suggest probably doing factors every time is probably easier, because if you write those factors, each of them is much simpler than the function itself. I mean, it's not going to be every time an exponential function, I'm sorry, the linear factor like these. So we cannot always expect that, but when you could, you reduce to the simplest possible factors. Just like if I have, I don't know, 100, I factor it into the simplest factors, which is, what is it, 2 times 50, 2 times 2 times 25, or 2 squared times 5 squared. Okay, so that's the decomposition of numbers that shows you what's there in the simplest form, and the same with factoring. So that's where factoring comes into play, and it becomes a tool. So and then you solve it, each of them separately, figure out. So that's the sign. I solve the problem of indicated here. Determine the sign of the derivative. Well, instead of determining the sign of the derivative, initially I determined the sign of its factors. Only 2 factors, so I determined the sign. Very simple. Do you remember each of them is a straight line, and it has one x-intercept. It's negative to the left, positive to the right. That's what's to be expected. And then you just go vertically every time like this, and just the simple rule: negative times negative, positive, and so on. Okay, and then you have all your signs available, and then this is the answer. Not the answer, but this is shortened right in the middle. This is the shortened version diagram giving you the data that you have had. Okay, so we are not trying to say too much. It is very easy to do too much, and it is tempting to draw a nice line, and then it might be easily incorrect. So that's why those arrows are actually very descriptive, because there you do not say too much. You're not saying anything. Remember, we talked about the concavity. You don't know which way concavity goes until you're done with that, and you proceed to the next stage. So this is okay answer. You draw three arrows, and if there are no holes in the domain, you can connect them into a curve, maybe. But otherwise, these are 3 arrows is all you know about the function. Okay, so by the theorem, positive derivative gives you positive, giving you increasing the behavior, and negative gives you negative. Okay, so the second example was pretty much the same, except the function was simple. Look at it. It is also to be expected that the derivative could be. It has the same exact sign, and so it's decreasing. but separately on these two intervals, and that's why, because there's a hole in the domain. Okay, so then, and then that's roughly your graph. The concavity, this is certainly, these are concavity I did draw it with concavity and indicating down, but it is more of a guess because you cannot be sure. That's why I like to use this thick highlighter, so that the line that I drew is very crude. Hypothetically, it could have been like this. You don't really know. All we know that it is decreasing. Does it have any particular concavity? Maybe not. We don't know at the time being. So this is actually would be an answer that is okay because of that. So that is mostly the initial step of analysis. All we need to know about it. Initial stage of first stage of analysis, which is the derivative, and then the next one we'll proceed to the second derivative. But let's maybe make one more example. So another example is, say, f of x is equal to x e to the x. So, well, as you can see, that one is going to call for the product rule. And we, once again, step number one, differentiate. So product rule. So don't jump to conclusions. I mean, we are moving forward fast, and so we kind of assume that we know we can do it quickly, but maybe we can't, which means that you have to do it in a careful fashion. So what do? You decompose your functions into two products, say u is equal to x, v is equal to e to the x, and then you know that uv prime is equal to u prime v plus uv prime. Okay, so that's the product rule. The cross multiplication of derivative times the function. Okay, so then to proceed in that fashion, you'd have to now have the derivatives. So I have u prime is equal to 1, v prime is equal to e to the x. Okay, and now these four functions are combined in my formula. Okay, so and cross u with v, u with v, v with v with and then v with u. Okay, got it. And v with v. Okay, u and v, and then v and u. Okay, got it. Okay, so so if I substitute now, what I get is u prime 1. So that's the first term is here. Okay, so it will be 1 times vertically e to the x, and the second one is the green one. It is x times e to the x. Okay, so that's my derivative. Differentiation is done, and I could leave it as this, or what do I do with it? So differentiation is the first stage, but why? Remember what we're gonna, the next question is gonna be determine the sign of f prime of x depending on x. Okay, so the beneficial, the best way to have a function that is easy to deal with in terms of its sign is to factor it. Okay, so factor it. Why? It's like well, because plus is plus, minus plus, plus minus, and minus is plus. Okay, so that's a very simple rule, and it doesn't matter how many factors you've got. You can use this rule as many times as it takes and find the sign of the product. Okay, so we factor it instead of keeping as is. I will factor it. It's easy to factor. what do I get?
E to the x times x plus 1.
X plus 1, or 1 plus x. Hey, let's make it 1 plus x. 1 plus x. So well, linear factors cannot be further factored, and the exponential function cannot be either. So these are the two factors. I list them, and once again I'll determine their signs separately. And I'm sorry, this is 1 plus x. Okay, so 1 plus x, very simple linear e to the x first. What do we now know about the sign of e to the x?
It's always going to be positive.
Always positive. So this information comes very handy. You just, in your mind, there should be this kind of picture. E to the x is positive, so right away you have all pluses, never equal to 0, defined everywhere. Okay, so these are the issues that you have to deal with. 1 plus x is equal to 0 at negative 1. So in other words, what I did, 1 plus x set equal to 0, solve, and I have x equal negative 1. So at negative 1 over here, we have 0. And then just think about this function, 1 plus x, it will be negative to the left and positive to the right. That's all there is. Okay? And so my function, not the function, the original function, but the derivative, now we go in vertically in this fashion, and determining the signs, and they will be minus, minus, 0, and then pluses. Okay? And that does it, because now, based on this, and the theorem that I have, I can now give you the behavior, not the sign, the monotonicity, right? So once again, I take a big arrow and draw it down, and big arrow, draw it up. It is a very crude sketch of the graph, but you can imagine that they are kind of connected in one curve. And if you want to, you could try to plot the graph in that fashion. Let me do that. So this is x and y. At negative 1, it is there's a tip. So it might behave like this. Okay, so there is a monotonicity down and then up. It appears to be there is a minimum point. Where exactly we don't know yet, so we would have to actually substitute the value so to find out where that minimum is. But well, you could, but this is really the important part. Is we have extracted all the information we could from the derivative, and now we have our function. So this is certainly what I'm talking about. This is y equal f of x. You could plot the derivative as well, but then it's not necessarily easier. Especially when you have this few factors. Okay, so any questions about this? So what do we do with those wiggles? So what do we do with the wiggles? I draw only wiggles because we don't know. There might be wiggles. As long as it's decreasing, it could decrease. That's an increasing function on the right, and yet it has this wiggling behavior. Okay, so what do we do about them?
Find out where slope equals 0.
Well, look at it. There's no slope 0 anywhere. That picture on the right, it's never equal to 0. It is keep going up. It just does this like a fish. Right, but that would take a while, a lot of points to actually determine if to tell where if any there are wiggles like that. The answer is look at the slopes to begin with to come up with an idea what is a wiggle, and this is a wiggle. Okay, the function is increasing. I drew it intentionally so that it is increasing. The function is increasing, right? But it has a wiggle, and it tends to the right. Okay. And all you have to do is just to look at what happens to the slopes. So you see what's happening to the slopes?
It's decreasing.
They're decreasing. So the slopes are decreasing is what tells us that there is a wiggle, and in not wiggle in one particular way. This is called the concave down behavior, but well, the opposite certainly is also possible, like this. Oops. What happened here? Like this. So once again, you can literally draw a few tangent lines, and it takes just a couple, and you can see that the slope may have been 1, then it is, well, like 1/2 slope, then slope 1, and then slope 2. So these are the slopes, and they are increasing. Okay, so the opposite behavior, and it's called concave down. I'm sorry, up. Okay, so it's either sloping up or sloping down, which has nothing to do, now that's the another kind of a thing that you want to assume, and you should resist. It has nothing to do with increasing behavior of the function itself. So the function could increase and yet remain concave up or down. So this is the picture to keep in mind. So increasing concave down, increasing concave up, decreasing concave up, decreasing concave down. Okay, so all these 4 possibilities are available. So once again, so increasing here, decreasing here, and here concave down, concave up. Okay, so and there's certainly the third possibility is in fact what's the minimal maximum. So for example, concave down or concave up. So that already suggests the last picture. The last picture is certainly it falls under this category of concave up and concave down, and suddenly actually with concavity tells you whether or not it's maximum or minimum, right? So this is a minimum and this is a maximum. So the concave down, the exact opposite, okay? The exact opposite, so concave down. What did I do? I messed up everything. Let me get started over. Okay, so up. Okay, we'll erase this. Okay, concave, increasing, concave down, concave up. Okay, decreasing, concave down, decreasing, concave up. Okay, so concave down give me the maximum, and concave up give me the minimum. Okay. So slopes, this picture is certainly to be remembered, what's on the right and how slopes are changing. If you remember that they could be negative or positive, what we're telling is happening is it's entirely about the direction of the rotation. So for example, if I go with concave down, okay, so what I have here is it is about, imagine that you're driving on this road, okay, and you are looking at where your, what is the meaning of the tangent line? It is in which direction the headlights are pointing. Okay, so you can actually tell. You see what's happening? Imagine that you're not looking at this road from above, but you are in the car. What are you observing with that picture on top left?
Which point's the car? What are we looking at?
Well, the orange lines are the tangent lines. They are also headlights. Okay, so if you're sitting in the car, what are you seeing?
That we're straight.
No, it's not. It's not straight. The road is turning, right? So as you can see, the headlights actually point out at your point of view. If you're looking straight forward, usually when you turn, you turn your head too a little bit, but the headlights are pointing forward, off-road, right? So that's actually a typical situation. So they make them like this, but generally you can tell imagine that there are trees. Well, suppose this is the road, and now I am a driver. I don't know. This is the road, and I'm a driver here, sitting, driving. Okay? So, you see what's happening? And these are, say, a bunch of trees. So what do you see? What are your trees doing?
You're getting hit by your headlights.
Right. Yeah. Yeah. So.
They're reflecting the light.
Right. But the point being is that well, if you imagine that you have the same situation, but you're sitting here, you're driving this way or driving that way. What's the difference is between the two situations? Is that in which direction the trees are moving. They will be moving to your left. If you're the case on the left, you're turning right. The trees will move to your left, right? So you're looking like this, and then you're turning. Yeah. So the trees will be passing your view to your left. So in your field of view, they're turning left. And these will be, if you have trees here, they will be turning right. So that is the difference. Even though you are driving pretty much the similar type of road, you will be observing very, very different behavior. Well, actually, if I want to compare that picture, probably is, let me take this picture. So. Okay, so let me do that. So this is what you're going to see is you are driving like this on this road. Okay, so and then you see trees. Yeah, you still see trees here. Well, yeah, I guess my guy is in the wrong place. You see trees here, and they will be moving to your right. Okay. So that is the difference is then not only the trees is one way to detect what I'm talking about, and what I'm talking about is the direction of the rotation of the tangent line. So in this case, I have one line, and then the second line. So this is the first, and this is the second, right? And then my rotation is to the right. Okay. In the second case, I am starting here. That's the first one, and the second one is here. So as you can see, I'm rotating counterclockwise. And that is the only determination. So because and that is determined by the concavity, because now if we move to the second row, we're still thinking about headlights. Okay, and then as you can see, which way we're turning. Clockwise, okay, and on the other hand here, we are turning counterclockwise. So that's the difference between concavity. You either think in terms of trees in front of you in your side of view, field of view, or you think about the headlights, which way is turning, and then if you're looking from above, but it's a bit hard to detect the rotation when you're not only rotating, you're also moving forward. So that's why it's kind of makes sense to actually think about as if you're in the car. And it still applies here. Yeah, still applies here. So this is one, and this is the other. You look how much it has turned. In the middle, it becomes 0. So it was positive slope, 0 slope, negative slope. That is rotation, which once again is clockwise. And here, negative, 0, positive. The rotation is counterclockwise. So clockwise here, counterclockwise. Okay, and there is actually a physics behind it, and that is what makes you rotate. What makes you turn on the road. And the answer is acceleration. So if you're driving on a straight, suppose your speedometer is at the same number, say 60 miles an hour. Okay, so then if you're going straight at 60 miles an hour constant, there is no acceleration. So this is no acceleration, 60 miles an hour. Okay, but if I'm turning, okay, it's still 60 miles an hour. But what makes you turn? And the answer is either you can say it's a force or you can say it's acceleration. Acceleration turns you left. It changes the velocity, right? So velocity is those slopes, those tangent lines are the velocities, and they don't change on their own. Acceleration changes them. The acceleration is the change of the velocity, right? So that's why those rotations are produced by the accelerations. So acceleration rotates the velocity. Okay, and so it could be one way or the other. Well, technically, this to fully understand this, we would have to study like a two-dimensional situation, like driving on the road on the plane. But just the idea that it has something to do, the change of the tangent line has something to do with the second derivative, I hope is clear, either rotation or that kind of physics situation. And then so as you can see, this is pretty much explains everything we need. We will say then f. Remember this, f double prime of x is f prime of x prime. Okay, so the second derivative. And the second derivative of the location is the acceleration. Okay, so that explains why it's happening the way it does. So so that's the second derivative. So it is the derivative of the derivative. So it is the rate of change of the rate of change. And the rate of change is nothing but the slopes of the tangent line. So how much those slopes change is the second derivative. And in fact, the sharper the turn is, the bigger is the acceleration. You can feel it, right? When you're driving, you can feel how the forces pull you in a particular direction when that turn is happening. There is a simpler way, I guess, just worth mentioning is not incremental. If you have incremental change, so that the same diagram I have here, is it complex? Maybe it's not that complex, but it just in case, you can explain concavity with nothing but 3 consecutive points. So let me do that like this. Okay, that's all. You're moving from first point from left to right, from first, second to third point. Okay, and maybe this. I will let me make sure that I have it done in the same way to match. So I don't think I did. So increasing concave down, increasing concave. This is I made it concave down up. So okay. So increasing behavior is visible, right? Increasing. In either case, you have increasing, but at the same time, you see that what has happened to the slope. The slope has decreased. So increasing. The way I did it was increasing concave down. If I have increasing concave up, it will look like this. Only 3 points, once again, you need, and then concave down decreasing will be like that. So all the concepts are still applicable as far as these two concepts applicable even when the motion is incremental. Okay, so in here I have so up, concave up, and this is decreasing. And so I have decreasing concave down. No, that's decreasing concave up. Okay, concave up. Okay, so once again decreasing concave, but the slope, you can see how the slope changes. When you have it's not a continuous process, which might be complex and maybe other factors coming into play, and there are infinitely many points, infinitely many moments of time. So you don't have to worry about that just to understand concavity. This is how you understand concavity. It's all here, and you still can explain concavity of like this, whether or not the concavity can be explained as whether or not your graph lies below or above the chord. So you connect the first point with the third point and see where it lies. So concave down if the chord lies below, or it is up when the chord lies above. Okay, so that's concavity for you. There's really not much else. Okay, so now we're using the second derivative. We know what it means in terms of concavity. We have a rough picture. We have also the definition, literally decreasing or increasing of the slopes, and we can apply that to the examples that we just had, and we can really get rid of those wiggles. Okay, so let's do a couple of these problems, because frankly at this point these are incomplete. The analysis is incomplete of all of these problems, is incomplete because the picture is still rough, even though as far as optimization is concerned we probably are okay. All we need is a minimum maximum point, so we're fine, but still better off if we do it right. Let's do the well, we could do all of them. I don't have room here, so let me do 10x and all the way through 10x. So f of x is equal to 10x. We already done this. F prime of x is negative 10x squared. Okay, so x not equal to 0. Once again, these two are treated separately. Okay, so then we have discovered that the conclusion was that f is decreasing on negative infinity 0 and f decreasing on 0 infinity plus infinity. Okay, so remember this. This is what we're saying about the function based on the derivative, because it's all negative. Now next stage we'll look at the second derivative. So second derivative, the power formula still applies. So negative x negative 2 prime. What do I get for the second derivative? 2x negative 3, right? Okay, so let's see. So there's only one factor. We can determine it is undefined. So I put an empty dot here to indicate that the function is undefined. So there's a gap in the domain, but to the left, I'm plotting f double prime here, to the left of 0, what do we know about the second derivative? Well, when x is negative, what can we say about x negative?
The y value is going to be negative.
It will be negative, yeah. It's simply a cube, right? This is 2 over x cubed. So the sign is the same as the sign of x, so it will be negative. And then it naturally becomes positive to the right. And then once again, okay, so we can write it verbally about f. Well, let's write it about f prime first. So I can write slopes decreasing, and here slopes increasing. Okay, so that's what we have found out, and then I could actually have once again a little diagram here to indicate if it is a slope down, like this. Once again, this is just let me use the big one. Once again, to emphasize that this is a crude tool, a crude way to visualize it. So that's why I'm using the highlighter. Okay, so slopes decreasing, but then they're increasing. Okay, so I'm not saying there is a minimum here, maximum there. I'm just indicating the concavity. So that's all I'm trying to say. So concave down, 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 right? Same word. Concave up. Well, it's not the same word. That word was decreasing actually, so it's not the same word. Decreasing, increasing, concave up, concave down. We cannot have a plot without using the information from stage 1. So this is stage 2, where stage 1, this is stage 1, the derivative itself. So we have to combine this information with the information that we got from stage 1. So from stage 1, we know it's decreasing and then decreasing again after a gap. Okay, but this time we know more. It's not only decreasing, it's also concave down. So this is the information that we want to take and create a better picture. So decreasing concave down will look like this. There is no wiggling anymore. Because the wiggling means change of concavity. That's wiggling, changing concave up, down, up, down. And then, so there is no wiggling, decreasing concave down. And the second one, decreasing concave up. So it will look like this. Okay? The only thing remains is to go even way back to the very beginning to know which way these two branches of the graph, how they located relative to each other. Okay, so in fact, so that's extra work, just plotting points, as it was suggested anyway. Plotting points will reveal more precisely what's happening to those graphs, and these two, what's happening to where these two branches are located, and this is where they are located. Oops. And then, if necessary, once again, don't forget all the rest that we have learned, and that in particular asymptotes. This function has asymptotes. So sometimes looking at the first derivative, second derivative might be insufficient, and then you look at the asymptotes as well. Okay, so let me do the other one, the example that I did previously with the with the exponential function. Where's the exponential function? Here it is. Okay, so you see this wiggling. Let me just append this computation with the second derivative. Okay, so let's compute we need to differentiate this one more time. So ex plus xex, f double prime of x is ex plus xex prime. Okay. Ex, the derivative of the first term. What's the derivative of the second term? Product rule. Product rule, in fact, the derivative we just computed, the derivative of x e to the x, was just computed a minute ago. Not a minute ago, but in the beginning. So this is the computation right here. So the answer will be, once again, ex plus xex. Ex plus xex. Okay, and then once again I factor because it's helpful. Okay, and you can see the difference that the factoring is similar to this, right? Except if this factor is different, it will be 2 plus x, and 2 plus x means that this thing will have zeros elsewhere. It will have a 0 at -2 over here. At -2, the second derivative hits 0, and it's negative to the left and negative to the left, positive to the right. So concave up, down, and concave up. Okay, so that doesn't look right. 2x. Hold on. What did I do wrong?
Is it decreasing and increasing?
No, this is the second derivative. This is the second derivative, and it is indeed negative for x is less than negative 2, and then positive for x is, I don't think I differentiated it right. X, e to the x plus x to the x, so that's our function. The first derivative is right here, ex plus x to the x, ex x to the x. I differentiate e to the x to the x, e to the x, x to the x, 2 plus x to the x, and it is 0. Well, okay, so no, yeah, actually it is possible. Then it is the picture might suggest something else, but so concave down, decreasing concave down, like this, and then increasing concave up. That's not right.
Is there going to be a hole at negative 2?
No way. I see. Okay. So negative 2 is the changing point. So okay, let me plot quickly, and then we'll finish next time. So up to negative 2, it is decreasing concave down. Then it continues to decrease, but becomes concave up. Oops, like this. So this is 2, and up to negative 2, negative 1, and at negative 1 it becomes increasing. Okay. Okay, we'll finish this next time.